So welcome to the last video about understanding NMR. And here what I'd rather do is I would like to utilize a strategy that I use whenever I have a subject that is very comprehensive or sometimes confusing. Usually what you would do is you would study the material and then solve questions. But what I like to do when we were talking about a very massive comprehensive material, I would like to take a look at the questions and then use them to understand what type of ideas I need to prepare myself for. So it's kind of attacking it from the other end. And this is basically the best thing that I would advise doing. So I collected all the questions that I found in all the manners that I found, which is not a whole lot, and because they do tend to recycle those. So we're just going to do some problem solving, and hopefully based on the last couple of videos you'll be able to have a nice intuition as to what answers we may need. So let's get started. I'm going to scroll one question after the other. And this is a relation analysis question, and in case you do not know what a relation analysis question is, we have one statement, and then we have a because, and then we have a second statement. What we need to figure out is whether the first statement is correct or maybe the second statement is correct, and if they're both correct, are they explaining one another? Is the because, are they relating? So let's try and do that one piece at a time. And if you would like to, and I would recommend trying to solve them on your own. So freeze the video now if you want to solve this on your own. Okay, so let's get going. NMR spectroscopy uses an electric field. We know that in NMR, nuclear magnetic resonance, we do not use an electric field. The only electric affinity we have there is the radio frequency electromagnetic pulse, and we only use it for its magnetic component. We don't really use it for its electric component. So NMR spectroscopy uses an electric field, I would say magnetic. This is how I would fix it. This statement is incorrect. Let's look at the second statement, because NMR uses non-ionizing radiation. And we know that NMR uses radio frequency radiation, and radio frequency is by far not ionizing. So I would say it uses non-ionizing radiation, correct. Perfect. And we're going to slowly scroll down. We have another relation analysis, and they're all going to be relation analysis because I found them to be the most difficult. So now what I would like you to do is I would like you to freeze the video at this point and read the question in case you want to tackle it on your own. Very well. In NMR, there are more spin states oriented in an anti-parallel manner because those spin states are in a higher energy state. So let's just defer back to what we had. We had spin states aligned with the magnetic field and spin states aligned against. These are all against. And these are all with. Now these are the anti-parallel, these are the parallel. So in NMR there are more spin states oriented in an anti-parallel. That would be incorrect. Less spin states oriented in an anti-parallel manner. And those spin states are in a higher energy state. And when we're talking about the anti-parallel spin states, those spin states, they are indeed in a higher energy state. So the second statement is correct. Very good. And we're going to keep on trucking. And again, this is a good time to freeze the video if you want to work on solving this question on your own. All right, let's keep going. Chemical shift in NMR is a shift in the nucleus's frequency due to chemical interactions with its environment, because NMR uses a magnetic field gradient. Let's take a look. We know that chemical shift affects the nuclear resonance, and it is also in the minimals, but it does not really, there's no frequency that we can associate with the nucleus. We associate spin and resonance. So if I'd like to correct this, chemical shift in NMR is a shift in the nucleus's resonance due to chemical interactions with its environment, and this would be entirely true if I fixed it. So this first statement is incorrect. NMR uses a magnetic field gradient, and this is a common mistake when people think, oh, magnetic field, it's correct, but it isn't in fact. A magnetic field gradient is, if this is my tube, a magnetic field gradient would be a magnetic field apply in a stronger well, in a stronger amplitude in one place than the other. It is not uniform throughout. A magnetic field gradient is a magnetic field, may look like so, which its components are actually more focused on one point. So this would be incorrect. What does use a magnetic field gradient is MRI. So if I fix this to saying MRI, this would be correct. Also, MRI uses a homogeneous magnetic field as well. Let's keep on going. And NMR, and again, this is a good time to freeze the video if you'd like to try and solve it on your own. So let's get started. Very good. In NMR, we can attain information from the resonance of spinning nuclei because a zero net nuclear spin is associated with them. So let's take a look. In NMR, we can obtain information from the resonance of spinning nuclei. And we know that when we fire the radio frequency, we have a drop in the spin, and slowly it would relax back, or the spin lattice will recover, and then there will be an emission of energy that we can read. So yes, we are getting information from the respective resonances of spinning nuclei. And a zero net nuclear spin is associated with them, and by them they mean spinning nuclei. And we know that spinning nuclei have a net nuclear spin that is not zero. If I'd like to fix this, I would say because a non-zero net nuclear spin is associated with them. So the second statement is incorrect, while the first statement I would say is correct. And we're going to keep on trucking, and you can pretty much really see what the spirit of things is. This may be the last one, I'm assuming, is it? Not sure, we'll see in a second. So this is the time to freeze in case you want to work on this question. Very well. In NMR, a homogeneous magnetic field is used because nuclei used in NMR do not have a magnetic moment associated with them. So this is first and these questions just break it down. Let's take a look at the first statement here. In NMR, a homogeneous magnetic field is used. Correct. There's no dwindling around. This is right off the bat correct, because nuclei used in NMR do not have a magnetic moment associated with them. And you may think, well, we need a magnetic field because maybe we do not have a magnetic field. But the first thing that we learned about spinning nuclei, this is my spinning nuclei, it has a charge and it's spinning, and it is a physical law that when you have a charge that is moving, it is associated with a magnetic field. So nuclei used in NMR have a magnetic field moment associated with them, or a magnetic moment associated with them. And this is how I would fix it. The second statement is incorrect, while the first statement is correct. And I believe this is it. Am I correct? Yes, this is it. Perfect. So if you understand why these questions were answered the way they were answered, I would say you are very well comprehensively understanding this subject, and all you really need to know is the different questions that were answered. What do they focus on? What is my level of understanding that I need to have to basically be able to answer questions about NMR, and an understanding. This relation analysis is the basic understanding format of a question. Does one statement explain another? Is one true? Is the first true? Are they related or not? So basically, if you can answer these questions, and these are the hardest questions, and that's why I chose them, you're good to go. And I would generally recommend attacking a subject, or attacking even all subjects, from this end to that end whenever you're talking about the biophysics subject, being that it is so widespread. It is impossible to focus on everything. So hopefully you found this understanding NMR videos helpful. and I'll see you in the next video.